continuously sending out signals, right? And then you need a second antenna to then continuously receive the signal. That's typically used, to, for example, here for velocity measurement. So you have two antennas. One is constantly sending and one is constantly receiving, and then you can measure the speeds very well. However, continuous wave radar is not used in remote sensing. Okay, what we're using in remote sensing are pulse radar systems. So we send the signal in pulses, and then we also receive them. This has the advantage that we can use only one antenna. We can use the same antenna for transmitting and receiving, right? So we transmit in a pulse and then we receive the pulses. You just have to make sure, right, that at that time when you transmit a pulse, you cannot listen at the same time to a pulse. Okay, so when you transmit, you cannot receive at the same time. So there have to be, the timing has to be in a way that when you receive, after you transmit your signal, it gets scattered back, and then you receive the signal at another time when you send. You can't do both at the same time. So your timing has to be very good, okay, when you design the system. Now, we have monostatic and bistatic system. Monostatic means you have one antenna which transmits and receives, while bistatic means you have one transmitting antenna and two receiving antenna, while multistatic, that would be another option, multistatic would be one transmitting antenna and multiple receiving antenna. Now, for most of today, or of the whole lecture, we will be talking about a monostatic system. That means we have one antenna, we are transmitting and receiving with the same. However, we're gonna talk a bit about bistatic systems as well, because they're also very much in use, especially for DEM generation. And in the slides, when I showed you the SRTM system, SRTM is, for example, a bistatic system. All right, we're still at the very basic level of EM signal interaction, so electromagnetic wave and the interaction. Now, this is something that you could see at every remote sensing class. Okay, here the very basic interaction of the electromagnetic waves, where we send in the signal at a certain incident angle, and then that can be reflected. The signal can be reflected. It can be absorbed by the object, right? There can be transmission through the object, and we also can have emission from an object. And all of that is also true for microwave remote sensing, right? So we see our signal coming in at a certain incident angle, might be reflected away, might be absorbed by the object. And we also have emission, and we are analyzing emissions with passive microwave remote sensing systems, who are only looking at the emission in the microwave range, which is also an interesting research field. We will not touch that much in that course. We will be focusing on active systems, but this also exists, right? And so, depending on the roughness of your object, right, of the ground, the signal will be mostly reflected back or away. So when we are having a signal and we are reaching a very smooth ground, a very smooth surface, then most of the energy will be reflected, like typically in 90 degrees or in incidence angle rate. Go angle away if you're looking from the side away from the sensor, or if you're looking nadir, then directly back to the source. However, if you have a rough surface, if you have a perfectly rough surface, the energy will be reflected with similar strength in all directions. Okay, so that is then called a diffuse scattering. Now, in radar remote sensing, we'll come a bit to that later why, but in radar remote sensing, we are always looking to the side. And in that case, if you have a very smooth surface, as you see there up, your signal will be reflected away. While when you have a rough surface, like some of the energy will be reflected back to you, to your sensor. So when we have a monostatic system, that means when we use the same antenna for transmitting and receiving the signal, then what's happening if we have a smooth surface is we receive basically nothing, right? Because all the signal will be reflected away from our wave, because our sender, the source of our electromagnetic energy, is also where we receive that. So there would be a rather black pixel, even although the reflection is very strong, but it's very strong away from our sensor. But if we have a rough surface, the reflection coming back to the sensor is very small, but there's something coming back. There's something coming back, and that we will see then in the radar image, typically in rather gray values, mid-range of values. Right. However, we have to understand that our roughness, what we understand as rough and smooth, is in relation to the wavelengths. That means if we have a 2 centimeter wavelength, let's say that road is still rather smooth, okay? That will react as a smooth surface, like a mirror, okay? However, that field on the left side, that's not smooth for 2 centimeter wavelengths. However, for 20 centimeter wavelengths, that's starting to get smooth. Or if we go to P-band with about 1 meter wavelength, that would be a smooth surface with respect to a 1 meter wavelength. Right? So what is smooth and what is rough has to be seen with respect to the wavelengths we are using. Now, in all systems that we build, in all electromagnetic systems, right, we have on the left side, we have a theoretically perfect impulse response, okay, of a signal, while in reality, what we can build and what we achieve is rather an imperfect impulse response function, which is typically in such a sinc function that you see here. Now, that is also the case for camera systems, okay, and other observation systems. However, in radar remote sensing, we are seeing that much more clearly because we have actually less objects that are reflecting and less backscattering targets that form our impulse response function. So we can sometimes see it very clearly in a radar image that each of these targets that we see is actually an imperfect sinc function, which is not perfectly at one point, right, is infinitely small, but actually has a certain width and has forming these side lobes to the side, which can then be forming noise and other unwanted information in our image. right? This is just a 3D look of such side look of such an impulse response function, because in reality we're gonna have that in 3D, actually even in 4D, because they're also time variant. All right. Okay. Now let's talk a bit about radar. And I use we're not talking really about ship detection, okay? Although it's a very important application, I'm gonna use ship detection to introduce a bit into how SAR works, okay? Now, ship detection is still a very important tool for radar, also for SAR systems, very widely used. For ship detection, we need to be able to differentiate the water from ships very clearly, okay? And actually, as I showed you in some very beginning slides, radar was designed for that, right? The first radar patent, the telemobiloscope, was designed to detect ships under bad weather conditions, because it's very suitable, okay? Typically, ships will reflect very strong, and water is rather dark in a SAR image, so it works rather well. Why is that? Okay, now let's take a look at these scattering processes. On the top left side, we see the scattering of the electromagnetic wave on something like calm water surface. We have calm sea, the water is very calm. Okay, our signal comes from the satellite, it hits the water surface, water reflects very good. It is a mirror to radar signals. So it reflects the energy away from the sensor. You don't get any energy back to the sensor. So your pixel will be black. Okay. If we have our signal and we have a very rough surface, the energy will be reflected in all directions at the same strength. Right. But that means a tiny part of it, a little part of it, is coming back to your sensor. And that's enough. That's something that we can then detect and see. Right. Now, why are ships so bright? Why are they so wide in SAR, which is because of this so-called double bounce effect. So here it's an example of a building, but it could also be a ship in the water. Okay, so our signal is moving down, it hits the water surface or the road in front of the building. Okay, and it gets reflected away. That's like a mirror, it's reflecting it away. But now the signal hits the building or the ship. Okay, that's also reflecting it very strongly, again, like a mirror. And now that forms, by the geometry of it, now goes directly back to the sensor. So now we have the situation that's a lot of energy is now actually reflected back to the sensor. This is so-called double bounce scattering. So you have two bounces. The signal is 2 times reflected and then reaching back to the sensor as a very strong signal. And that sounds a bit like a strange case, right? You have 2 bounces, it hits there, it hits there. But it happens very commonly, right? When we look at cities, we have lots of double bounce reflections from road to building, back to the satellite, and the other way around, from the building to the road, and then back to the satellite. It's very common. Ships also reflect like that. And it's also the reason why we saw in that early image from the H2S radar why that city looked so wide, because there's lots of these double bounce reflections happening in urban areas. So the pixels are getting white. Okay, so we have lots of white pixels there. So although it looks maybe strange, we need 2 bounces. It's very, very common. Okay, you can even have 3 or 4 bounces, and we show some examples of that later on. Now, the appearance of your SAR image clearly depends on the wavelengths you're losing, right? Like different frequency they look differently. Like blue, it looks different. The blue band looks different from the red band. Okay, similar in radar. So I'm not going too deep into it, but it is very clear. It depends a lot on the wavelengths you're looking at. So you need to be aware of, let's say, at least which wavelengths you're working with. Okay, there are huge differences between X band, which would be 3 centimeter, L band 20 centimeter, and P band 80 centimeter. There's a huge difference in the wavelengths in orders of magnitudes. Okay, so but we want to talk a bit ship, detecting ship. So we established the water will look, calm water especially, will look very black in a SAR image. And the ship, because it's metallic and reflecting back, having a lot of small edges, will look rather white in a SAR image. But we are not only interested in detecting, we maybe also want to see how big is the ship. Can we determine the ship size based on the radar signal? And yes, we can. So because the radar signal gives us information about the area. And now I would wish you could see my cursor and I could show you that, but I'm really not getting that done today. So let me talk through it and you have to watch it a bit. Okay, so at the beginning, we are transmitting our signal with a certain strength, right? And that's one of the advantages that we have with a radar, is that we are making our own signal, right? If you have an optical system, you rely on the sun, right? You have no control about the energy that comes from the sun. Okay? You can't control it. But with your radar system, you can, you know the power that you have, that you use to transmit it, you know the polarization of the electromagnetic wave, you know the phase that you send it out. All of that you know. You have very good, complete control over the signal that you're sending. And we can use that. We can use that to form then real equations of it. All right. So we're sending out a signal with a certain power, the transmit power, right? And then at a certain distance of air, we get a power density at that distance. And that power density, you see, is the transmitted power divided by 4p r square. Now 4p r square, what's that, right? For those of you who do not remember that, like me, I had to look it up, right? That area of a sphere. The area of a sphere is 4p, and the radius of the sphere squared, right? So if you imagine that, right, the signal that you transmit, and then it expands like a sphere along the range, and then at one point, at a given distance, you're getting that part, right, of that sphere, of the area of that sphere. So it makes also geometrical sense if you think about it. We have also the antenna directivity gain, G, which is a description of how good the antenna that you use is able to focus that energy. Okay, it's like we can focus the energy more than just that sphere, which would be a totally unfocused energy, right? So the power density at the scattering object that you're looking at is a bit higher because we can multiply it by G. And then now we have A, which is the power intercepted by the area of your object. That would be the area, for example, of the ship, right? The size of the ship would be A, okay, or the size that is visible from the radar of the ship, right? But this is basically a function of size. And then the fraction of power that is returned to the radar, which would be a function of the material and of the direction, so how much of that is actually coming back to the radar system. Then we are going back, radiating isotropically back. You see that's another sphere, right? We can understand it as another transmission now backwards. And then we receive that at the receiving antenna, and the power that we actually receive also depends on the area of the antenna at the end that is receiving all of that. And if we put that together in one radar equation, you see that the received power, PR, depends on the transmitted power, the area of our antenna and the antenna gain, so the features of the antenna. Then the area A, the area of the object we are looking at, and the part of the energy, the percentage of the energy that is reflected from that. And then it's divided by 4 pi square and r power of 4, which is, we're losing a lot of energy, right? R, the range, power of 4, we're losing a lot of energy when we are going away from our sensor. But it gives us, with A, it gives us a description of the area, the size of our object, and basically we can use that to have an estimation of our size of the object we are looking at, because we know all the other parameters, right? We know the antenna size, we know the antenna gain, we know the power we transmitted the signal, we know the range, and we know the power we have received, right? So we have a function of the object size, and we could use that to estimate an object. And if you know a bit about airborne radar, they also give these signals in sizes, and then they describe, for example, they describe a stealth fighter to be in the radar signal as small as a bird or something like that. They give you that description in sizes, right? Because we understand our signal and the radar cross-section that we receive as an area size, and it's typically given in square meter. Let's take a look at that with an example that's from the ARS system. So if we transmit a signal with 4,800 watt at 850 kilometer distance, we illuminate our footprint, the whole radar footprint at 70 square kilometer. We say about 4% of the signal is returned back to the radar. You see that's not much. And we have an antenna area of 10 square meter. What we then get back as received power is 6.5 times 10 power of minus 9 watt. So you see we only get a little bit energy back. We transmitted 4,800 watt and we receive 6.5 10 power minus 9. So that's a huge difference. That's 100 dB difference between what we transmit and what we receive. So there's a huge difference in the power level. So we transmit a lot of power, but we receive only very, very little of that power. But that is enough to make our image, right? Just the difference between transmission and reception power is very huge. We must make sure that we keep our signal to noise ratio then above it, because you see the received power is actually very small. So there is danger of low signal to noise ratio in principle. And it also shows you that we work a lot in radar with this decibel. We use large power ratios, so we use a lot of decibel. Actually, the decibel, which is a power ratio, is actually not such a great, it's not such a great unit, okay? Because actually it's a ratio of one power to another power. We use it a lot in radar because we like the log scaling, the logarithmic scaling of it. but it's not such a great symbol because what is the ratio of it? And typically we just define it as a ratio divided by 1, so to 1 square meter, right? That's what we use, and then we form the dB scaling of it. Now, what you need to know about it is that depending on the data you have or the software you use, it may give you the dB, the decibel scaling in the image, right? But on the other hand, for many equations, we need numeric scaling, right? So it is quite often necessary for you to convert that. The reason I mention that is it's not uncommon that people make the mistake and not doing that. Okay, right? That's how it is, right? So keep that in mind that for most of the equations you are seeing, you cannot use the dB scaling. Okay, you have to convert that to numerical scaling. Now, controlling the radar cross-section, the backscattering of your signal is very important, right? In this case here, for military applications, it might be very useful and welcome to reduce the radar cross-section. So this is here, you see in the foreground is a stealth ship, which has the goal to have a very small radar backscattering, right? In the background, you see traditional ships, which do not have a small radar backscattering, right? And so here the goal is to reduce the radar, that the signal is coming back to the sensor, and you can also see it's quite clear how that is done, basically by avoiding edges as much as you can, right? And by tilting this, by having a lot of surfaces that are not perpendicular, also not perpendicular to the water surface, so that they make sure that while the energy is reflected also away from that stealth ship, but it's reflecting not back to the sensor, not back to the original, right? It's reflecting away in another direction. So, however, the ship is still reflecting a lot of energy, and it also gives you already knowing that the ship would still reflect a lot of energy, just not going back to the sensor would already give you a way on how to defeat stealth technologies, typically by having multiple receiving antennas spread out. One of them will receive that signal coming back. So with an array of antenna, you would see that ship even very, very clear, because if you have one receiving antenna that is going in that direction, that's in that direction that ship is reflecting to, it would be even a very strong reflection. So, right, but controlling our radar cross-section is something that in ships and airplanes is something that is important. And another way of controlling that is also to increase it, right? Here we have another example that ship, it's not a military ship. So what they want is, they want to be seen in a radar system, right? They don't want to be overlooked. So typically most ships, they try to increase their radar cross-section. And we see on the right side, this is such a corner reflector that is mounted here on top of the ship that will give a strong reflection in all directions, so that that small reflector reflects probably stronger than the rest of the whole ship. So making sure that the ship is being seen by radars, so to avoid accidents. Okay, so that's very common that you find such reflectors on ships so that they get be seen more clear, which is typically the goal, right? You want to be seen with your ship to avoid accidents. Now we talked about the water being black in some images, and there are also many algorithms and applications which are built on the assumption that water is black in some image, and that is true as long as you have calm water. But if you have waves, if you have sea waves, and here's an example with some stronger waves around an island, you don't have a calm sea anymore, you have waves, and waves may reflect energy back. And that energy can be actually even quite strong. And, you would have now probably a problem detecting at least smaller ships in these waves. So it is not always true that water is black, right? Calm water is black, but water is not always calm. So that is just a reminder of that the reality is a bit more complicated, okay, than just saying water is black and ship is white. Okay, it's not as easy and not under all circumstances. Now we have here these artificial targets, or these, you can also say these archetypes of targets, right? We have a mirror, so that would be, for example, a metallic plate that we orient directly back to the sensor, so the energy comes in, gets reflected back. Be a very strong target. Or this dihedral, which is basically any rectangular perpendicular form, where we have then this double bound scattering. Trihedral and corner cube, which form then there you will have even 3-time scattering, which gives an even stronger signal then. And these are forms that where we build artificial targets in that form so that we can find them in the SAR image, but we also find such forms in nature, right? Typically, actually not really nature in that sense, more like man-made objects. We think about, we find a lot of dihedrals, rectangular forms, perpendicular forms in man-made objects, right? We like to build such cubes, okay, buildings and so on. We like to build perpendicular. So we will see them a lot in, it's not really nature, okay, in man-made areas, okay, urban areas and so on. Or we build them sometimes, especially to be seen for radar, okay, for validation purposes, for measuring purposes. So we see these mirror, corner cubes, trihedrals, bihedrals, you see they're all in use for radar remote sensing. And we have one advantage of that we can actually calculate theoretically how strong should that reflection be. Now, it's a strength of radar remote sensing because we know our wave and we know the power we transmitted the wave, the power we receive, that we can actually calculate how strong such be. You can't do that with optical remote sensing. So we can calculate a mirror of that size should have this reflection strength, the dihedral of that size should have that. And we are using this information, and you can use that to have in your radar data to have an estimation of what is the size of the object you're looking at. But it's also used to validate and to calibrate your radar system, okay, setting up such well-defined targets with a well-defined size and then calibrating the signal according to that. All right, but let's talk about resolution, okay? We talked about how can we define the ship size by the signal strength, okay? But if I have a high resolution image, I can also measure the ship size, right? It's even better. Now let's talk about how we can achieve resolution and what resolution we can achieve. So In radar remote sensing, we have to separate the two directions of our image. They actually have very different meanings. So we have one is the range direction. That's the direction in which our signal is traveling. Okay. And the other is the azimuth direction. That would be the signal our sensor in this case is traveling. So if we look at that slide, the azimuth direction would go in and out of the screen. Okay. Right from the screen toward me or away from me. And the range direction is on the side of that screen. Now in range, we measure the position of an object by looking at the time the signal is traveling. So we are transmitting the signal here with t1, time 1, it's traveling. You see the first building, the signal is coming back earlier than the second building. Right? The first building comes back something like t8, the second building will be like 9, 10, 11, several time steps later. So by looking at when is the signal coming back, we can differentiate where are they, where is the object. Now in azimuth direction, we can separate the images, right? If they are not in the same radar lobe. Now the radar itself is not like a laser, okay? It's not like a small beam. It's actually a rather large lobe. We can't really make that very, very small. We'll discuss that soon. So in this case, if we are very close to our radar, here to our airplane, we can separate here that black point from the two gray points. But if we are more far away, we couldn't separate these 3 points from each other because they would be in the same lobe in that case. So it's the angular resolution that is important here. And we can here make an example with the human eye. Right? If we go a distance of 700 kilometers, then we could maybe differentiate object with maybe about 70 meters. Okay, we would have a resolution of about 70 meters. Now, if we take a look at the radar system at that, we have 5 centimeter wavelengths, and we say we have an antenna of 10 meters, we would get an angular resolution of 3.6 kilometers, which is, not very good. Okay, it's not a great resolution. And in range, right? In range, the resolution we can achieve, that depends on how short we can make that pulse. Okay, if we can have a very short pulse, right, then our resolution gets better. And it's just the pulse time, pulse duration times the speed of light divided by 2 because the signal is traveling there and back. Right? We often have this divided by 2 because we have a signal that travels there and back. Okay. So if we assume a pulse duration of 40 milliseconds, which is a realistic number, right, then we get a resolution range of about 6 kilometers. Again, these are both very low resolutions. So that cannot be the whole story. Okay, because otherwise with resolutions of 4 kilometers by 6 kilometers, that would not be very nice. So how can we improve that? Now, in range direction, we need to reduce the tau, that signal pulse time, the signal duration. But it's very difficult to do that while sending also a strong signal. So it's very, technically, it's very difficult to send a strong signal just for a very short pulse time. But what we can do is we can change the frequency of the signal during transmission, right? So we can change the frequency, for example, with a linear increasing frequency during the signal. submission. So that is also known. If you're old as me, you still remember radio, good old times, right? And we had AM amplitude modulated radio and FM frequency modulated radio. And the frequency modulation is what we're talking about here. We are modulating the frequency of our signal during transmission. And in radio, the frequency is changed during transmission, and then you have a decoder, your radio at home or in your car, right, that decodes that frequency changes into music then, right? Instead of using the amplitude to get to the music signal, we can use the frequency as well. And in radar, we're doing the same thing. We are changing the frequency, in this case linearly, changing the frequency over the pulse. And if we do that now, we change the frequency of the pulse, and then when we receive the signal, right, we are just checking, at which frequency did I receive the signal, right? And I know, this signal is from the beginning of my pulse, when I first send it out, this is at the end of my pulse, because it has a different frequency. So by analyzing the frequency, now the effective tau depends only on the bandwidth now of my signal, how much frequency bands I use, how much bandwidth I have. And if we use 20 megahertz, for example, now we get a 50 nanosecond tau, which gives us then an effective range or a resolution of 7.5 meters. Now, controlling the azimuth resolution, we have to control the antenna size, right? So the larger our antenna is, the smaller we can make that beam, right? So if you want to have 20-meter resolution from 700 kilometer away, we need an antenna size of, if we calculate it, 1.8 kilometer. That's not possible. Okay, we cannot have a 1.8 kilometer antenna in space. That's just not going to work. So how does it work then? So what we are doing is we are forming a synthetic antenna, right? That's where the name of synthetic antenna radar comes from. We're forming a synthetic antenna. And that synthetic antenna is formed by using the motion of our sensor, the motion of the airplane, the motion of our satellite. Okay, so we are traveling, the satellite is traveling along, it's not jumping actually, it's traveling linearly along, and we are sending pulses out while we travel all the time. And then we combine these pulses, okay? And what then happens is, if you look here at the screen, okay, so from T1 to T3, that one point in the middle, that area where all of these radar lobes overlap, that is, we can see that area from T1, from time 1 to the end of it. So all of these pulses during that time can see that one point. And now by taking all of these pulses and putting them together in a computer, for example, there are different ways actually to do that. You could even do it without a computer, but right, nowadays we use computer for that. By putting them together, okay, we can now build an antenna which is so long, from taking the distance here from T1 to T3. So we form an antenna along the flight line, which is very long, which is as long as the time that the sensor is traveling here from T1 to T3. So we're forming then an antenna that is easily a kilometer long or something like that. But a synthetic antenna formed of the pulses along the way. Now, the length of that synthetic antenna, that depends on the resolution of the real antenna, right? And if we combine all of them, and in the equation, right, the resolution that we can achieve is now only defined by the length of the real antenna divided by 2. So there is no distance anymore in it. How can that be? If you look again at that screen here, okay, if we are very far away from the sensor, okay, we see that point that is seen by all the from T1 to T3 is longer. Okay, if we would move that point more close to the sensor, we could not see it from T1 or T3, only from T2. And if we move it more far away, we would see it longer. So if a point is very close to the sensor, you see it only for a shorter time. So your synthetic antenna is shorter. And if the point is more far away, you see it for a longer time and your synthetic antenna gets longer. And these two things just cancel each other out. So that at the end, your resolution is independent from the distance. Okay. So the resolution of a SAR system and only depends on the length of the real antenna divided by 2. So if you have a 10-meter antenna, you can get 5-meter resolution, and by the bandwidth of the system. Right. If you have a very short antenna, your beam is very wide. If you have a very wide beam, your synthetic antenna gets actually longer compared to your real antenna. That's why a shorter antenna gives you higher resolution in that case. Okay, it's a bit you need to think a bit about it why it's not that clear at the beginning. Right? Another way to understand that, if we not really think about forming that synthetic antenna, we can also understand the resolution in azimuth with the Doppler effect. Okay, so we can use the Doppler effect. So our point that we're looking at here, that black point, from T1 to T2, we are moving towards that point. Okay, we are moving toward that point. At T2, we are next to that point, and then afterward, we are moving away from that point. So the Doppler signal, the Doppler frequency is changing from moving toward the point to moving away. So by analyzing the Doppler frequency shift, how is the signal changing, the frequency is changing, we can identify the time when we are next to it. Okay, that is the Doppler 0. We are next to the sensor, next to that point, and now we are moving away. So we know where in azimuth we are by analyzing the Doppler, and that's also, analyzing the Doppler is also independent of your distance, right? You can analyze the Doppler independent of the distance. And so you can understand the synthetic antenna by thinking that we're forming an antenna that's getting longer and longer, or by thinking it as a Doppler effect. We're using the Doppler, the frequency change of that returning signal, to analyze the distal position. Both is valid understanding. It's mostly implemented as a Doppler effect in the system. But there actually, if I remember it right, there's like 6 ways or something like 6 ways to build a synthetic antenna and understand the synthetic antenna radar. And these are just 2 of them. As far as I know, most are nowadays implemented just how that process is via the Doppler effect. Right, and if we have the Doppler effect, we are also analyzing the frequency change, right? And we can understand that as another chirp signal because it's also actually a linear frequency change of the Doppler signal. So we have a range chirp signal and an azimuth chirp signal. And the advantage is that both of them are then also processed very similarly by comparing them to a reference signal. And so in range and azimuth, you have very similar processes in actually implementing it and processing the data. So if we look at that here, in azimuth, right? We're seeing here, that's how that would look in then the real raw data of a single point. We are moving toward it, and away from it, the frequency is changing, and we can then pinpoint the 0 Doppler position of the target. So then, now I know at this point in time, I'm next to that target. And as long as I know the position of my airplane and the looking direction, I can pinpoint the position in one direction. And in range direction, I measure the time of the signal and actually the frequency shift in the signal there. So SAR is a two-step imaging process. So you acquire the data, and for a single point, you get lots and lots of reflections, lots and lots of signals, lots and lots of samples, and then you have to process the raw data to get to a usable image. This is not really a usable image, right? So the raw data that you get looks something like here on the left side. You need then to compress that in range, and then you compress in azimuth, and then you get here a SAR image where you can see something, right? And most of you typically will start work on this already focused data, but you can also get from some sensors still raw data, which then you would need to focus by yourself with help of some software to get there. Right. This is a slide I actually never know where to put, I have to say. Wherever I put it doesn't fit. It also doesn't really fit here, but it's important to talk about it, to understand a bit how satellite orbit work, right? We send our satellite up, and then they are rotating around the Earth, right? And typically we use such a sun-synchronous, such a near polar orbit, where we go more or less from north to south direction. And why are we doing that? Why are we using that is rather simple. Because if you imagine, it's always a question which one is stable and which one is moving. But let's say that our satellite orbit is stable, and if we are going in a near polar orbit around and around and around the Earth is actually rotating under our satellite, right? Day to night, you know, Earth is rotating. Okay, so we could say our satellite stays stable and the Earth is rotating under it. And in that way, you're covering the whole Earth. Okay, the satellite is going around, but the Earth is rotating under it, and you can, over time, cover data from the whole Earth. If you would put a satellite in another orbit, say at a certain latitude, going from east to west, that would also work. However, you would not be able to cover the whole Earth because you would stay on the same latitude, right? You would see the same point on the ground more often, but you wouldn't really cover the whole Earth. That's why most of Earth observation satellites and most of SAR satellites actually go in this near polar orbit. So that means we have two times where we can see, two orbits where we can see the same point. On the Earth, one time we are ascending, so going from south to north. Okay, that's the ascending orbit. And then we're coming back, we're going down on a descending orbit, more from north to south, and as the Earth is rotating. And that's one time we can see it from an ascending orbit, and one time we see the same from a descending orbit. The same is true for optical satellites. However, if you have a nadir view, if you're looking down, there is not a huge difference between ascending and a descending orbit. However, in SAR, as we are looking to the side, we are looking at from a very different angle, and the images may look very different, right? And we are coming back to that again, but you need to know these are the two main directions that we have from satellite SAR remote sensing. If you have an airplane or UAV right? You could fly whatever you want. Okay, you would not be bound to just two directions. Okay, now SAR systems are unfortunately a little bit complicated, right? But they're also very flexible. Flexibility means often complicated, right? So these two things go hand in hand. But what do I mean by that? So the typical SAR that I described by now is the so-called strip map mode, and that means we are flying along and we're sending out our pulses along the flight path. And I hope you can see the video that looks then something like that. So we are flying along and we are collecting the images typically along the flight path and with range direction perpendicular to the flight path. That's the standard mode. That's the so-called strip map mode. However, if I can shift my radar looking direction a bit, I can do things a bit different. So if I'm able to switch my looking direction of my antenna a little bit forward and a little bit backward, like we call that squinting, I can squint forward and backward, I can create a spotlight mode. In spotlight mode, I start the sensor looking a bit forward, and I fly around and I look now a bit backward. Okay, so I look a bit forward, I fly and look backward. So I'm looking more long time at the center. What does that mean? It means that now my synthetic antenna gets even longer because I look now even more long time at the center point. So my resolution gets higher. I get a higher resolution image at the center. However, as from here, I'm looking forward. I don't see here, and here I look backward. I don't see here this side. So I'm having higher resolution, but I'm not seeing all. I'm missing some areas, right? But I get at the center of it with a higher resolution, which can be interesting if, let's say, I'm interested in a city and I want to have a high resolution image of the city, but I don't care about the areas around it, right? And I can use spotlight mode. In the video, it looks then something like that. So we start looking forward, we end looking backward, and we get a smaller image part, but with higher resolution. Right. Now in ScanSAR is another mode. In ScanSAR, to make ScanSAR, I need to be able to switch my antenna, not squinting forward and backward, but be able to switch up and down to change the incidence angle of my antenna during flight. If I can do that, then I'm looking a short time at the first swath nearby, then I look a short time in the middle and a short time behind. That allows me to increase my swath size. I can look at a larger area. Okay, so I can see more. But at each point, I look for a shorter time. So my synthetic antenna gets smaller. So my resolution gets smaller. So in ScanSAR, I have a less resolution, but I can see a larger area. While in Spotlight, I have more resolution, higher resolution, but I see a smaller area. Right? So ScanSAR, you want lower resolution, but more coverage. That looks then something like that. We are switching our looking angle along range direction and have a larger coverage then. That is, if I want to see more area. Now the problem of the ScanSAR mode is that you are not, in Spotlight, we are gradually shifting our antenna. In ScanSAR, we are looking at one swath, we call it one angle, and then we stop looking at that, we switch the antenna, we look at another angle. Stop, switch, look. There is a small time where we don't receive, where we don't get information, right? Because we need to switch the antenna. It's not a gradually switch, it's actually like a stop and then go again. So that can lead to some missing lines in the image and some missing data. So people don't really like that. Okay, so to improve that, we have the TOPS mode, which is a bit more complicated. TOPS, just to remember that, is the opposite of spotlight, the opposite of spot. So if you read TOPS backwards, it's actually spot. Okay, because in TOPS it is a scanner mode, but it also changes the antenna in the looking direction for each burst. So what is happening in spotlight mode, we're looking forward while we fly and then we look backward. In TOPS it's the other way. We look backward and we fly and then we end up looking forward. That means now we're even looking a shorter time at each so-called burst. Our resolution gets again smaller, but why we are doing that is now we are looking backward, we end up looking forward, we switch, the next burst we are looking backward again. So we have between these bursts, if you look at that, we look between burst 1, burst 2, we have an overlapping area at some time where we look at this area between these two bursts from both sides. Right? And then we have an overlapping area. We set them up that we overlap also between these swaths. So we overlap in all directions, and we can use that overlap to get rid of this missing data. Right? If we from one burst, from one swath, we didn't see some area because of the switching, we saw it, we catch it another time. Right? And then we can get rid of that. And so we get a seamless image, a seamless scanner image, a more beautiful scanner image if you want. Now the TOPS mode is very important for many of you because that's how the Sentinel-1 system operates. That's the way how Sentinel-1 gets so large coverage. And some of you may know that. We will talk about it because Sentinel-1 is a system from ESA which provides global data, and for all of us, even more important, I would say, provides the data for free. So you can just download the data. So it's very popular data, and it is acquired in this TOPS mode, which is a bit more complicated to process. So I need to mention that even if it's a rather complicated and strange operating mode, you need to at least to be aware of that. Even if you do not understand everything, you need to be aware, this is in TOPS mode processed. So it's the handling of the data will be a bit more complicated than in the standard strip map mode. Now this is an example of Sentinel-1. You see in the TOPS mode, we can get a huge area coverage. This is like one stripe covering a huge part of Italy in one stripe. And if you put several together, you can cover the whole country with just a few images, with just a few acquisitions. So that is the advantage of the TOPS mode. Now we have to talk a bit about also some more annoying things like speckle. What is speckle? So speckle is what makes these SAR images so ugly. Okay, so I mean, I have to say they're not very beautiful and not very nice to work with. So speckle is coming from that we have several scatterers in one resolution cell, in one pixel, and that's called speckle. So because we have here a coherent system and these different scattering centers, they superimpose, and these small elementary radius scatters, they may add each other up or cancel each other out, depending on their position, depending on their phase, and the relation of the phases to each other, which then causes this Speckle effect. So important is to understand that that is a signal, right? The speckle itself acts like a noise, but it's actually a signal, and it's not noise. That's to say, if you take the same image at the same time from the same position, or let's say not exactly at the same time, right? But if all the properties are still the same, all the scatters are the same, your speckles information is also the same. Okay, so it's not really a noise. However, as things are changing on the ground, and you also, if you fly or you're in a satellite, you're not really coming back to the exact same position again. You're not getting the same results. So it acts like a noise, you can say. Now, the speckle is just of this superimposition here. Many years ago, oh my God, that's a long time ago, I made a stupid small example. So I put here just simulated that I put in each of these pixels in each of the resolution cell, I put the same amount of scatterers, okay, same number of scatterers with the same amplitude, but at different positions within the cell, right? So each of the cells, each of the pixels has the same number of scatterers with the same amplitude, but inside the cell there are a little bit different positions. And now from the results from them overlapping each other from these signals and canceling each other out depending on their position, right? You get this phase noise, you get this speckle noise already, and you see it's quite strong noise-like effect. And it depends on, even if they will have all the same amplitude, but because they don't have the same position inside the cell, their coherent sum is different. And that makes a huge difference in the appearance and the beauty of the image. Say, if we look on top, such a star image is unfortunately it's very, very noisy, right? It's the speckle noise that makes it, yeah, well, ugly, okay? And below down optical image, it's not only because it's the same wavelengths like our eyes, so we clearly can understand it more easy. It's just more smooth because it's not suffering that strongly from the speckle effect. What we can do to get rid of the speckling is we can multi-looking, right? For example, if we have on top, we have a single star image. On the bottom, we average over a huge number of star images, right? We can remove that, right? We can remove that by averaging in a process that is then called multi-looking. For example, here it's multi-looking in time with using several images, but also we can do it in space. The word multi-looking, why we say multi-looking, not just averaging, is a SAR-specific term. If we can achieve this smoother image by separating our antenna in separate looks, by just each look processing just a part of the synthetic antenna, getting then one look with a lower resolution, but we can get, for example, here 3 looks, each of them is lower resolution, and then we can average between these 3 looks. That's how we can achieve then 3 independent measurements and then averaging over them. That's one way to do it. Another way to achieve the same, very, very similar effect is just by averaging with a box window or something in the image processing. Okay, and then in SAR we still call that multi-looking, although it's then just averaging. Okay, but it's just a SAR specific term that you need to know to understand what we're talking about. Typically what we mean by that is averaging over several pixels. I should have showed you that slide a little bit before, Why I mentioned that many times, SAR systems are always side-looking. Why is that? Well, they didn't even explain that. If we would build a SAR that's looking down, we have a rather huge SAR lobe. It's not a very small laser beam, it's kind of a huge lobe. So the left side and the right side of that lobe on the ground will reflect back at the same time. We couldn't separate these two. We couldn't separate the left side of the image from the right side of the image. So we have ambiguities, and that is then useless. So we need to look to the side so that we can separate, that we can position our, that we can identify the position of our return by the time they're coming back. So that's the reason why we have to build them a side-looking system. They cannot be a nadir-looking SAR system. That's just not possible. We have to operate them as side-looking system, which causes us all kinds of trouble. Okay. So, in terms of radar reflections, we talked a bit about that. Right? We have the diffuse reflections, we have specular reflections, and we have these corner reflections, which are quite common in SAR and gives us these very bright pixels then from urban areas or from ships. Right? And we also have to talk about the geometry of them, because our signal, the position of our object in this range direction, that depends on the time the signal is traveling. Now, if you have a flat Earth, right, we can position that very, very clearly. Okay. But in reality, we have topography. So if we have a mountain, the top of the mountain is closer to our satellite than the bottom. Okay. A higher point at the same X position, if you want, is closer to our satellite. So that leads to foreshortening, which means that the front side of that mountain, the side that is closer to the satellite, gets shortened in the image, and the backside gets stretched in the image. In the extreme case, it leads to layover. That means the top of the mountain is imaged now before the bottom of the mountain. The top of the building will be imaged before the bottom of the building, closer to the sensor, which is then a layover effect. Layover also is then ambiguous, right? Because now you get a reflection from the top of the mountain, from the top of the building, back at the same time like the reflection in front of it, which again leads to ambiguity. You cannot separate them. Most easy to understand, I think, is the shadow, right? If you look to the side, if we see the mountain, there's some area of the mountain which you do not get any reflection back because it's in the shadow of the radar, and it's going to be black. I think this is similar because it's very similar to optics, right? If it's in the shadow, it's in the shadow. Okay. That is the radar shadow then. All right. Let me see where we are at. Okay. Yeah, well, that takes me 1 minute. Let's make that our last slide for today. Weather effects. This one is actually the very first Terracer X image taken. And what we see on that is here in the red circle. That's actually clouds and a thunderstorm, right, that we see here. Now, I need to mention that because you're going to read that a lot. And I also said it, SAR images are weather independent. You can look through clouds, which is true in most cases. But if you have some very strong rain, right, well, water is reflecting, right? If you have very strong rain, that strong rain, especially in shorter wavelengths, may reflect back. And you have then here a white part, which is the reflection from the rain, and a black part behind it, which is the part where your energy, where your signal did not get through that rain. And then you see such weather effects. That is not very often, but it happens, especially in smaller wavelengths like X bands. You can have that effect. So if we have any questions, but thanks so far for listening. And let me see, are there any questions so far?
Professor.
Yes.
I actually have saved the questions in the Word file. So if you stop sharing the screen, then I can share those questions.
All right. That's good.
Okay.
Try to stop share. Okay. I think I stopped sharing, right?
Okay, then I try. Why I did not able to get? Okay, I share.
Yeah.
Yeah, these are the questions. So maybe we can move.
Okay.
Yeah.
Let's see if we can do them all today. I try to do them, but we can also maybe then, let me see. Let's just start. That's the threshold when you make deeper based on the range structure. Okay. Okay. All right. So if I understand the question right, do we need a different threshold for different terrain when we want to do flood mapping? So when you want to separate the water from non-water? And the clear answer is yes, because, you know, if there would be one magic threshold, right, everybody would use that. Okay, but the threshold may be changing, and it's also not so easy because so if you say there is one threshold, you assume your water, your flood water is smooth and calm. Now, however, flood water is not always calm. So you may have waves on your water. It may be rushing down. Right? There might be huge waves. And in that case, it might not even be very black, your water. Also, if you have flooding in vegetated area, if you have, let's say, you have some agriculture field, right? There is some crop growing and parts of that is now underwater, but parts of the crop are out of the water. That pixel will be even more bright than it was before the flood, because the mixture of flood and vegetation makes that reflection even stronger. So you have to be very careful, right? When you do that, it's very simplistic to say there is one threshold and waters are not always going to be black. The reality is going to be a bit more complicated. How good is Sentinel for ship tracking? Well, yeah. The next one, how well can Sentinel radar be used monitoring ships for intelligent purposes? It's actually working well. Okay, you can do that quite well. I have a student who is actually working on that and did do some machine learning to identify the ships. It's working quite well. It's getting difficult if you get close to the coast. So where do you separate them? But if you would have, let's say you have a clear water mask, no, here's water, here should be water. You can identify ships. Larger ships, very well, like larger metallic vessels, okay, container ships, tankers, you can find well. Smaller ships, sometimes not. For flood mapping in urban area, which band should I use? Well, you're going to have a hard time to find floods in urban areas, to be very honest, because there's lots of interaction with the buildings, and it's going to be very difficult to separate flood there, because if we say a road is underwater, okay, the road is normally also very black in a SAR image. Now is it now black from the water or black from the road? You probably won't really know, right? But you ask me about the band, then I would say, well, you probably need high resolution. So it's probably going to be X band would maybe be the best for that. Is there any relation between microwave bands and their ground resolution, right? I went to that a bit, and I did not show you that slide. I had that slide in another presentation. I cut it down a bit. Yes, now it is about the bandwidth. So your resolution in range depends on the bandwidth. That's how many megahertz of the band you can use. If you have a high frequency, so let's make an example. If you have 9 gigahertz in X band, okay, clearly taking 50 megahertz, 500 megahertz, even up to 1 gigahertz as bandwidth, where you can use the whole bandwidth for your resolution. That's possible. If you have then a very long wavelength with a smaller, lower frequency, right? If you just have 1 gigahertz frequency, you cannot take 1 gigahertz bandwidth. It won't work, right? So you will be limited, okay, by physics. So the longer your wavelengths, by physics, you are limited in the resolution you can get. But the main reason is not even the physics. The main reason is, depending on the wavelengths, there are limitations of how much bandwidth you can use. So the bandwidth, the radio signal bandwidth is limited because many people want to use that. Your mobile phone wants to use a certain bandwidth. I think they're normally operating in L band, and the TV signal is in P band. So the signal you can use for remote sensing, the bandwidth is limited based on where you are on that radio band, and it's more limited for L band. It's very limited for P band, and it's less limited for X band. So you will have higher resolution in X band than you will have in C, especially than in L, and in P is the lowest. Okay, let me see the time. I don't think we can answer all. I will answer the rest of them next time in the beginning. However, let me have one more, two more, okay? Let me go up a bit. Sishan, let me answer the next two, okay? Okay, wait. Yeah, it's an easy one. Number 9, is there any difference between lowercase r and uppercase r that I have used? And no, sorry, right? That is just me being not very careful when preparing, okay? That in both cases, that would be range, okay? That should actually be, I think, lowercase r. You know, slides are developing over time, and then sometimes they're not so similar. Can various band of microwave give different ground penetration? Yes, very clearly, yes. The longer your wavelength, the more penetration you will have, but you can typically not go very deep in the ground. Okay. All right. Okay. There are lots of questions. I will go next time in the beginning. Some of them are a bit, I have to think a bit actually. Okay. Okay, there's lots of polarization. Okay, let's do it like that. I will go on that in the beginning, in the rest of the questions, and take me more time for that. I'm happy I get so many questions. This is very, very good. Okay, keep on asking lots of questions. Use the time that we have. Now, for this moment, I'm going to stop for today. I'm very, very happy. I had lots of fun talking to you. I would have even more fun if we would be together, right, in a room, but at least like this, we can have still a bit time here together, at least. Okay, so I have lots of questions, but the time is a bit short. I will do that next time if that's okay for you. Join us again on Sunday, right, in 2 days.
Yes,
Sunday evening, Sunday afternoon for some of you, Sunday morning.
Yeah.
All right.
So before going, Professor, we need, can we take a picture or what we say?
Yeah, that's a great idea.
Together. Yeah,
that's
please,
a great idea.
Turn on your videos, everyone, please.
Let's try if we break Zoom. Okay, maybe we're killing it. Let's try. Oh, no, it's actually working. Surprisingly, I can see all of you. Hey, all of you. Okay, nice to see you. Okay, let's try and take some pictures.
Okay.
You probably have to do lots of screenshots.
Yeah.
Okay.
Okay. Thank you very much. It's okay, I think.
All right. Now, thank you all for listening. Okay. Keep on questioning. Also, tell Sishan, tell the BRGTC if you want, you know, what courses you would like, what other topics you would like. I think they're all interested in also offering you more courses, different courses, more practical courses, okay? Tell us about it, okay? We are trying to make it happen, right, Sishan? At least we're going to try, let's say. We're going to try to do that. But we need to hear from you. You know, if we have lots of people say, oh, well, you know, we want maybe course with more practice where we really can do that, then we get motivated in organizing that even online. We want to do that on site because like training with the software is better when we're all in a room. Okay. But if you have many people interested in that online, then we also can think about how to do it online. Okay. So, you know, or different topics, let us know. Okay. Let them know. Okay. I think it's a great opportunity and chance, and there are quite of good programs here. All right, I talk too much again. Bye-bye.
Thank you very much, Professor.
Bye-bye.
Thank you, Professor.
Thanks for joining.
Thank you very much.
Thank you very much, Prof.
Thanks, Prof.
Thank you, Professor.
Thank you very much.
Thank you, Professor Timo.
Thank you so much.
Thank you.
And Sishan, send me the questions then. If there are more questions coming,
Professor.
I will all try to answer them.
Oh, okay, Professor. Okay, I will send you the questions.
Please don't forget to send us the link to the video, please. We'll appreciate that.
For the videos, actually, I'm not sure if you will be able to get because, but yes, I will connect with the organization, and if I can send, of course, I will send you all.
I think that's still under discussion, but it's not. It's more a matter of the organizers and not so much of us from our side. Okay.
Thank you very much. But I think if you tell them that there are a lot of interest, I think that will be possible. Meanwhile, thank you very much.
I hope so. All right.
I think at least slides can be shared.
Okay. Anyway, I'm logging off. Bye-bye.
Thank you, Prof. Bye-bye. Thank you.